All right, hello everybody. Welcome back to data analysis from the syllabus lecture. So this is where we're actually going to begin the content of the course, be able to talk about some fun mathematics. So today we're going to introduce optimal prediction. The idea is that we want to predict one random variable from another, and we're going to actually just pin down what that means, right? What does it mean to do optimal prediction? Optimal by what standard? We're going to define the standard. And then we're going to talk about how to actually make good predictors sort of in a theoretical setting, right? And the idea is we want to define what our goal is, and then when we're working with data, we'll know what our aim is. So references, in case you'd like to follow along in the course text, this is the sections in Truth About Linear Regression that correspond to this lecture. So I mentioned this a little bit in the syllabus lecture, but I'll just mention it again. So the title of this course being data analysis, we could actually get much more specific because we're going to be almost exclusively talking about linear regression. So the course could be titled Intro to Statistical Modeling, or it could be titled Modern Regression. And the reason for this is that the tools that we're going to learn here are sort of fundamental tools that are going to serve as a foundation for when you do more modern statistical modeling and use more modern tools. So it used to be that a regression course was sort of taught with the purpose that you would be using linear regression as your bread and butter tool. That's not the case anymore because there are other tools which can be used instead and which often are used instead. But it still is the case that linear regression is a useful sandbox to test out your ideas because it's a fairly well understood regime. And so when we say intro to statistical modeling or modern regression, we're thinking about regression with the idea of extending what we learn in this context to future courses and other methods. So I don't mean to undermine linear regression and say it's not useful. It is. I will almost always start out doing regression in a data analysis problem because it's a good way. It's like, as I said, it's well understood and it's a good place to start. And so that's where you're starting in terms of your coursework. And so this class in particular, what does it mean to do regression? So regression is predicting a quantitative random variable from other random variables. Okay, so the big deal here is this word quantitative. Okay. So if you predict a quantitative y, that is a numeric y, is also a synonym, you are doing regression. If you're predicting a categorical y, okay, so y is a category instead of a number, you are doing classification. Okay, so that's the difference. It's y numeric or a categorical. So we're going to be almost exclusively predicting numeric random variables y. So quick question. Check understanding regression or classification. So the example here is we want to predict whether a certain individual should be granted a security clearance using two predictors, okay, their credit score and their number of Facebook friends who are foreign nationals. Okay, so let me make sure that I have that up here. So what is our predictors? Oops. So what are our predictors? X. Okay, so our predictors in this problem, we have two. There's a credit score, right? And there is the number of Facebook friends who are foreign nationals. Number of Facebook friends. We'll abbreviate, okay? And Y, oops, what we're trying to predict, this Y value, is whether an individual should be granted a security clearance. Okay, so suitability for clearance. Okay, so that is y is going to look like it's going to have two outcomes, right? That is yes, suitable, or no, right? So so parsing this into predictors, these are random variables that are predictors, and our response random variable, or the one we want to predict, we have y is a category, right? Y is not a number, y is a category. This x is completely doesn't matter in terms of defining this problem as regression or classification, but because y is a category, this is indeed classification. Another example, so predict the number of U.S. Navy sailors enlisting per year using GDP per capita uh, as the predictor. Okay, so this is a little bit poorly phrased, but what I'm saying is that GDP per capita. So what's the GDP per person per year? So you're going to use that to predict the number of folks who enlist in the U.S. Navy during that year. Okay, so it's sort of a measure of wealth, predicting the number of folks who enlist, and sort of the question is what relationship would we expect? Would we expect more spending? Maybe means more military spending, means more open positions and more sailors enlisting, or do we expect poor economic output or low economic output related to lots of people wanting to sign up for stable paychecks, right? So. But again, just like this above problem, so this is our Y is sailors per year, okay, and then X is GDP per capita, and so X, Y is a number, so this is regression, okay, so this is going to be our emphasis, the regression side of the house. All right, so the goal being, as we said, we're doing regression. We want to predict a numeric y. So what does it mean to do good prediction? Okay, so let's say we have a numeric random variable, y, so we're doing regression, and we have an estimator, y hat, for y. Okay, so how do we quantify the accuracy of y hat? So how good is y hat at estimating y? So to do this, we need to introduce some concept of error, and it's common to use mean squared error. Okay, we're going to get a lot of work out of this concept of mean squared error. So this is a very important concept. And so we're going to use this mean squared error to quantify the error of an estimator. And the idea is if we have an estimator y hat, which is estimating some y, then the mean squared error between y and y hat is the mean, the expected value, the expected squared error. Okay, so this is one of those nice definitions, which it's words actually just describe what it means. It's the mean, the expected squared difference between y and y hat. Okay, so that is the mean squared error, and what's going on here is, right, so these are random variables. So if I just take y minus y hat and I square it, that's a random quantity. If I take the mean, this gives me a number, right? But by squaring this, I'm turning this difference into something purely positive, right? Or excuse me, it's non-negative, right? Because it could be 0. So this is taking y and y hat, giving me a non-negative scalar as a measurement for how close y is to y hat. Okay, so this is how we're going to define optimal predict, or this is how we're going to say. So to do good as a predictor, y hat is we want it to have small mean squared error. Okay. So what are its attributes? The attributes of mean squared error, that is, we just discussed it is non-negative, right? Because we are taking the expected value of something which is non-negative. It is symmetric, okay? So what this means is that if y hat it overestimates y some certain amount, right, then the mean squared error is exactly the same as if y hat underestimates y by that same amount, right? So and this is just a property of squaring, okay? So this, as this comment here suggests, so certain applications, this symmetry is appropriate. Like I have the example is archery or darts or something like this, where you're trying to throw a dart y hat at some center of the target y, right? You're a little bit to the right or a little bit to the left. That sort of is similar in terms of your ultimate performance, right? But in some problems, like financial problems, it may not be appropriate to have this symmetry. For example, if you make more money than you expect to make, that's sort of a much better outcome than if you lose more money than if you expect to make, right? So if you have expecting how much you're estimating how much money you're going to make, You say, well, so what? This is not really a loss to me if I make more money. I'm concerned about losing money, right? So in some situations, like financial problems, this symmetric loss where overestimating and underestimating are treated as the same is not appropriate. But this is just a property of mean squared error. So it's important to keep that in mind when you're applying this to real world problems. The other thing about mean squared error is that it's smooth. So mostly for historical reasons, because of ease of calculation, you can take derivatives of smooth functions. Mean squared error was preferred over other types of error. So an alternative type of error to mean squared error is the mean absolute error, right? So you take the expected absolute difference instead of squared difference, right? But the absolute value function is not smooth, whereas the square function is. And so the analysis of mean squared error is actually easier than that of mean absolute error for this reason. And so the smoothness is going to come into play later as we talk about how to derive optimal estimators. And so speaking of deriving optimal estimators, that's what we turn to now. So question, what is the best constant valued predictor of y? Okay, so I have y is a random variable, and I want to find the best constant predictor. Okay, y is random, we want a constant. So we have a notion of best because we've defined an error. So if we want to have the best predictor, we should have the one with minimum error. Okay, that is mean squared error. So we're going to find the constant m which minimizes the mean squared error between y, the random variable y, and some constant m. Okay. So just using the definition of mean squared error, right? We can go ahead and expand it out, or we can write it as this expected squared difference, and I can expand this quadratic. So remember that expectation, you've seen this in your probability course, but expectation is linear. So what that means is I can apply the expectation to each part in this sum. Okay, so I'll apply the expectation. What happens if we apply the expectation to m squared? Well, m squared is a constant, so it's just as m squared. We can pull out constants from an expectation. That's due to the linearity of expectation. So we sort of are applying expectation to each one of these terms and pulling out constant as we wish. We can't pull out the square or anything crazy because that's not how expectation works, right? You can't pull the square out of the expectation. You can just pull constants and distribute across the sum. So this is a simplification. And so we want to minimizing this expression is the same as minimizing this expression down here at the bottom because we've just simplified. Okay. So how do we minimize this? Well, y'all know how to take minimums of smooth functions. You take a derivative, right? So we're going to apply some calculus. So we're going to minimize this expression with respect to m. We're going to take a derivative with respect to m, set it equal to 0. That's a stationary point, and it's going to be either a minimum or a maximum. Because this is concave, this is a convex function in m, so you can draw it, and the coefficient of m is positive, so it looks like a quadratic like that. So stationary point is a minimum. But you can actually take a second derivative and show that it's indeed a minimum and not just a stationary point, but we'll just do the stationary point calculation. So take a derivative, set it equal to 0. What do we get? We take a derivative here. This is constant. It has no m's in it. The m drops off here. This 2 comes down, becomes a 2m. So we're left with this equal to 0. That's setting the first derivative equal to 0. We can solve by dividing up by the 2, adding over the expectation of y. We see that m is equal to the expectation of y. Okay. So what we've just shown, barring a little bit where I was a little bit informal about why m is a minimizer and not a maximizer, but what we've just shown is that the expectation of y is the constant which minimizes mean squared error when we're predicting y. Okay, so that's kind of nice. The expectation sort of falls out naturally there. So what happens when we want to predict y from another random variable? Okay, so instead of predicting y with a constant, we want to predict y with another random variable. Okay, so our estimate m of x is now a function of x, right? We just had m, which was a constant. Now m depends on x. So that is, you tell me I don't know, the humidity, X, and I'm going to predict Y, the temperature, right? So my prediction is allowed to be a function of my input, which is humidity. So we want to minimize mean squared error. Again, it's the name of the game. We're minimizing over functions m of x. So functions which take in that predictor x. Okay. So in this case, the best estimator is the conditional mean. Okay, so this might make some sense. So to minimize this expectation, it suffices to minimize it for each x, right? You're minimizing an expectation. You could just say, well, if you fix me an x, I want to choose the m which minimizes for each x, and then just do that for all the x's, and that will be my minimum. And if you did that, if you fix the x, right, then what happens? Well, for fixed x, this calculation is just reduces to the one we just did, right? You're taking a mean, but the idea is you're fixing an x. So the expectation becomes a conditional expectation once you've fixed x, and if you do that for all the x's, you get the minimum function. So the idea is once you give me a fixed x, it reduces to the problem we just solved, and the result ends up being the conditional mean because we're depending on an input x instead of just predicting a constant. So this reasoning here, these bullet points outline just in a little more detail what I just said. And so the recipe is basically, right, fixing an x. Once you fixed x, you know the name of the game. The minimizer is the mean, but that mean depends on the input x. We can see this as a result of as the law of iterated expectation. That's sort of fancy language, and I'm not going to go into that too much now, but this sort of can be formalized even more, but I think this intuition suffices for now. Okay, so we're going to conclude this lecture. So it's a very short one, just sort of getting us started on what does it mean to do well when we're predicting one random variable from another. And for us, that's going to mean small mean squared error. Okay, just highlighting what we've done. So we are talking about regression in this course, estimating quantitative random variables, right? We're going to do so with mean squared error. We talked about the constant predictor is the one which minimizes the constant predictor which minimizes mean squared error is the expectation. And if we have an input x, then what we want to do is find the conditional expectation. Okay. One more thing here. Why do we have to have? Why is? Let's phrase this a little differently. We have mean squared error here, right? And we're doing regression. Let's say we were doing classification, right? Where instead of predicting a quantitative random variable, we're predicting a categorical random variable. Does mean squared error make sense in that setting? Okay. So the answer is actually no. The reason is if y is a category, right? If we're predicting a category, what does it mean to subtract categories? Right? You can't that's not well defined for categories. If I say yes, approved for security clearance, no, not approved, you can't subtract categories. That's not defined for that type of random variable. And so when we restrict to regression, where we're estimating quantitative random variables, that actually allows us to define mean squared error, which we can't otherwise. Okay, so just a quick comment for why these two bullet points are related. Okay, so that's all I have to say for this time. So I look forward to seeing you all at the next lecture.